No, Miss Jones, I wasn't recording. Now I am.
I wanted to tell you, but they said I shouldn't. Like, tell you over the thing. I commented.
Oh, I see. Thanks. I'll do this again just in case anyone's worried about not being able to see this later on, getting your exam credit. I'll do it again. All right. Another maths question. Same thing. Taking out your numbers and using those numbers in the equation. Many people didn't get any marks in this question because they used gravity as 9.81 newtons per kilogram. When they give you a rate for gravity, make sure that you use the rate for gravity that they give you. Same thing could happen for acceleration. The acceleration of an object moving towards the core of the Earth is 9.81 meters per second squared. If they give you 10 meters per second squared, use that. We did this. We came out with an answer of 900 joules. State the amount of useful work done by the blades as the drone rises. My drone started down here on the ground and then moved up 20 meters. We don't actually have to do any equations, but just to help you understand it, work done is force multiplied by distance. The force that we're working against here is gravity, which is mass times gravitational field strength. Because my drone went up high, we can call that height, but distance is still the same as height. So the amount of work done, force multiplied by distance, is the same as the amount of gravitational potential energy that has been transferred to the drone from its motors and its whatevers. So the change in gravitational potential energy, delta EP, is the same as the useful work done, E. The same thing can be said if we worked out the kinetic energy of a falling object. So if we work out the kinetic energy of an object just before it hits the ground, that will be the same as the amount of potential energy when it was up in the sky. So if it has 100 joules, and we work out mathematically that it's got a gravitational potential energy of 100 joules, we know that the kinetic energy at the bottom, just before it hits the ground, is going to be 100 joules as well, assuming 100% efficiency, which we do at GCSE. Now, let's just say you messed this up and you said that the answer up here was 10. For whatever reason, you thought it was 10. We have these questions that are linking up together. In the GCSEs, if you make a mistake on one section, you don't get penalized for all the rest. So if you're in the middle of a question, you've no idea what you're doing, you realize that you've messed up your maths, don't panic. Don't quit doing that question. Because if you were down here had done 10 divided by 4 to give you the power developed as 5, you would have gotten full marks, even though it's 900 divided by 4. Because to find the power, it's the amount of energy transferred per second, 900 divided by 4, give you 225. So the correct answer is 225 watts. If you make a mistake here and you keep on trying, you'll still get 2 marks because you don't get penalized. All right, universally really well answered. Strong field lines, strong magnetic field. B is the answer. For the most part, this question was answered okay. Now, when I say okay, I mean okay in that most people got at least 1 mark. Some people went crazy, did lots of stuff there and wrote loads of lines and didn't get any marks for obvious reasons. Right-hand rule. Thumb goes in the direction of the current. Figure 7 shows a wire carrying a current. Draw on the card in figure 7 the magnetic field that is produced by the current. Because the current is going down, the right-hand rule says that my magnetic field is going to be going in the direction of my fingers. So the magnetic field, whoopsie, is going in that direction. You got 1 mark for getting the correct direction. Your second mark was to show that the magnetic field wasn't just around a small part of the wire, but that it expanded. So you got 1 mark for the correct direction, and you got the second mark for showing that there was concurrent rings that were going outwards, spreading away. 3 people I counted got this mark. Others may have gotten it from Mr. Patrick's marking, but only 3 people got the mark for writing the arrow in here. I'll come back to that in a second. Yes, sir. I'll have a look at the end and I'll see if you go up a grade. No worries. Yeah, also, let's just say that if you're looking at what you're doing and you think you deserve an extra mark, shout out maybe at the end when it's not being, televised or monitorized. All these words aren't the thing I'm trying to say. But I'll have a look at it at the end and we'll see just in case there's any extra marks. All right, this is FIBL, FBIL. Again, it's an equation. I'm going to skip it. I'm not going to go over it. I'm going to do a separate video on all these equations step by step showing it. If you want to just double check that you were given the correct answer, it was 0.18 newtons. Got some really creepy drawings for this. Some really good drawings and some really creepy ones. Fleming's left-hand rule. FBI, force on your thumb. B, magnetic flux density in your pointer. I, your current, your middle finger. Describe how Fleming's left-hand rule can be used to determine the direction of the force acting on the roller. Now, this is referring to this roller right here. Now, I'm sorry for everybody else who's watching this. I won't be able to communicate this to you properly, but the way that you write this down is arrange your thumb, your first finger, and your second finger so they are mutually perpendicular. That's the phrasing that we'd use for it. Alternatively, you can draw a diagram like that, label it thumb, first, second fingers. That's good enough. We had a lot of this stuff going on. Also good enough. This one is going to get the marks. This one is not. What's the thing that's missing? Labels. Now, FBI. The force is the thumb. Magnetic field is the pointer finger. Current is the third finger. That there is enough for 3 marks. A correctly labeled diagram will get you 3 marks. A non-labeled diagram will get you no marks. Yes? No. Hold. Thumb, first and second fingers perpendicular. Thumb equals force. First equals magnetic flux or magnetic field. Second equals current. Now you see the way I'm writing this. Hold thumb, first, second, fingers perpendicular, thumb equals force, first equals magnetic field, second equals current. That's actually exactly enough to get you marks. You don't have to be poetic when you're doing these drawings, or when you're doing these answers, okay? The arrow question was answered really quite poorly, but that's okay because it was a confusing thing. Mr. Patrick and I are going to make one of these to demonstrate it to you because there's mad crazy, yo. Look at this diagram. Current is going in, and then current is coming out. We now have the direction of the current. Just like Santa Claus, who lives in the North Pole. That's the worst Santa ever. Santa Claus lives in the North Pole, and he goes all over the world at Christmas time from the North Pole everywhere else to deliver his presents. So the direction of this magnetic field is north to south. We're going to arrange our fingers. FBI, perpendicular. I'm going to arrange my thumb so it's going in the direction of the current. I'm going to arrange my pointer finger so it's going in the direction of the magnetic field, which means my roller is being pushed in this direction because my thumb was pointing towards that direction. I'm 90% sure this won't actually be on your GCSEs, actually, now I'm thinking about it. We'll check at the end. I'll let you know. Okay, springs. Now, springs aren't on your GCSEs. We're not higher tier. We're not looking at springs for the GCSEs. I'm going to go through this quite quickly just because I want you to know where you made your mistakes and whatnot. This was answered really lovely. You were allowed an answer anywhere between 50 to 55 millimeters. How do we show the your context up here? Weights added to the spring as shown in figures 9b and c. Estimate. That means you don't have to be 100% accurate. You don't have to do any scale drawings or anything like that. If it said calculate, then you'd have to draw a scale drawing and then figure out the exact represented height that the spring is. The original length of the spring as shown in figure 9a. So there is my spring. I've added some masses. I've added some more masses. Draw a line. There's my estimate, 50 to 55. Weights are added to the spring. Describe how the reduction in the length of the spring when weights are added can be determined. Hats off to the human being. I can't remember who it was who wanted to bounce photons off it. I don't know if you were just having some fun, but it was a really nice idea. No. Measure original. Measure original. Take away compressed. 2 marks. Now, if you want to, you can pad it out. Measure the original length of the spring minus the compressed length of the spring. Happy days. But your examiners will reward brevity. Brevity being a big fancy word for not using 2 words when one will do. The irony of having to use more than 2 words to describe the one word that describes brevity. That's fun, isn't it? It's fun for me. Two ways experimental procedure could be improved. Right. Any kind of experimental procedure. When you talk about any kind of experimental procedure, we always have to think of epic rave. Because all of science is an epic rave. Think about the equipment. How could you improve the equipment? Think about the procedure. How could you improve the procedure? What is the independent variable that we have to measure? Is there a control variable that I can make better? And to repeat and find averages. Did anybody here write down the word repeat, but not average? About 6 or 7 people wrote down do repeats. You will never get a mark for just saying repeat. You have to think of rave. Repeat and average. So let's look at the equipment and the procedure that we're using here. Got a nice little ruler here, but I don't like this ruler too much because it hasn't got very good resolution. So to improve this piece of equipment, I'm going to get a ruler with millimeter divisions. And look at what I've done here. I've set up my ruler over here and my spring over here. And if I'm looking at that, now here's time to draw the creepy eye. If I'm looking at that spring dead on, then that's absolutely fine. I'm able to understand it. But if there's any parallax, then I'm not. So what I'm going to do is I'm going to move my ruler closer. As part of my procedure, as part of what I'm doing in this experiment, I'm going to move my ruler closer so that the areas of parallax are reduced. I can also add a little pointer. So if I make sure that there's a little piece of paper attached to my spring, actually, I tell you what, I'm just going to get rid of that. A little piece of paper attached to my spring, then I'll be able to see where that is on my ruler all the time. And also, I seem to have jumped from like 4 bits of mass here to like 8 bits of mass here. It'd be much better as part of your procedure to have more steps. The more steps you have in between, the better your answer is going to be. This equation was used, and the answer was calculate spring constant of K. Force of that, extension of that, calculate spring constant. I can't remember what the answer is. Does anyone get this answer correct? Can you let me? What? 38.5. Thank you. The next one, a lot of people wanted to use F equals X times K. If they tell you to use an equation selected from the back of the paper, please trust them. RTFQ, what does that stand for? Read the full question. If they tell you to read the full question, they tell you to use an equation from the list at the end of the paper, use that. I saw about 20 people use F equals XK in this equation. It was not one of the lists at the back of the paper. You do not get marks. Silly, silly. Please, please, please. RTFQ. Question number 5. Context. A student investigates resistors connected in parallel using a number of resistors. Each resistor has the same resistance. Figure 10 shows a circuit diagram with one resistor R. There. Add to figure 10 a voltmeter to find the potential difference across resistor R. Hello. It's absolutely fine. Leah Long, no, I've got Cody Tovey. I don't know where Leah is. They will be in 2S4, I believe. Yeah. Oh, Miss Jones, you're going to get a visitor in a second. Should have just said that, and then she could have gone herself. Miss Tovey, get ready to go. You what? Oh, she did. Quickly, someone from 2S4, go to 2S2 and get Miss Tovey. We'll help Miss Coulson out. No, don't do that. That's that. All right, back to this. A voltmeter to find the potential difference across resistor R. That's what I've done. Whenever something's connected across another component, it's always in parallel. You can't have something wired in series across another component. We want to add another resistor in parallel with resistor R. So we do that. State the measurements the student must take to find the overall resistance of the resistors in parallel. 2 marks. If you wrote down voltage, current, 2 marks. The command here was state. The context was this. The direction that they asked you to do was state measurements, so you know you're going to have to talk about something that you're going to be looking at, an ammeter or a voltmeter, that the student must take to find the overall resistance. They just want you to state the 2 things that you need to use to calculate resistance. Are we okay at the back? Another graph question. As X does something, Y does something. Linear, non-linear, proportional, or indirectly proportional. Use numbers. The student investigates how the overall resistance of the circuit changes when additional resistors are added in parallel to R. Context. Each resistor has the same resistance. Useful to know. Figure 11 shows the results of the student's investigation. We're looking down here. State the resistance of a single resistor. Yeah, 1, 1, 1. So there's 0 resistors, there's 2 resistors, there's 1 resistor. Resistance of 1 resistor is 1 ohm. Comment on the relationship between the overall resistance of the circuit and the number of resistors in parallel. Use information from figure 11 to support your answer. RTFQ. As number of resistors increase, overall resistance decreases. It's non-linear. Turn off that phone, or I'll get my magnet. At 1 resistor equaled 1 ohm. 6 resistors. It's okay if you've done very bad. You've got weeks and weeks and weeks and weeks and weeks. 3 marks for 3 sentences. This isn't even a sentence. That's just using data. As X increases, Y increases, X decreases, Y decreases, whatever. Is it linear, non-linear, directly proportional, indirectly proportional? Then use numbers from the graph. Calculate the potential difference across the 15 ohm resistor. Loads of people use 35 ohms for this. It's not what they were asking for. They just want the 15 ohm resistor. We have the current going through the 15 ohm resistor. Current will be the same because I1 equals I2 equals I total in a series circuit. The current is always the same in a series circuit. So I 0.2, R 15 ohm, V, I don't know. R equals V over I, giving you the answer. Has anyone got that? Thanks. Oh, I could have done. Okay. Now, here's where we had a little bit of problem. The resistance, please, Miss Layla, just the resistance of resistors that are in series are added together. R1 plus R2 equals R total. This is asking you for the power across the two resistors. Now, if you just use one resistor, you got no marks. If you incorrectly added together the two resistors, you get 2 marks. I'm not going to go through the full rigmarole, but don't forget the squared if you have an equation with a squared on it. Zero acceleration implies that your forces have to be balanced. These forces are not balanced. These forces are not balanced. These forces are not balanced. These forces are. Your answer was B. I'm not spending too much time on this either because almost everybody got it. This was answered quite well. Here's your context. Figure 14 shows 2 small boats pulling a much larger ship. Boat 1, boat 2, TNT ship. The ship is connected to the boats with ropes. The tension in each of the ropes is 20 kilonewtons. The ropes at right angles to each other. Draw a vector diagram and use it to determine the resultant force that the boats exert on the ship. Draw, command, direction, vector diagram to show the resultant force. Believe it or not, that was 2 marks, what I've just done there. 2 marks. That was 3 marks. And getting the correct answer of 28 kilonewtons, 4 marks. You could also have drawn your diagonal. Done the same, it's the exact same thing. Draw your diagonal, draw your intercepts. There is a video of this on YouTube. Search McKelvey on YouTube if you're not happy with your vector diagrams, and we can go over that. You can go over that in your own time, or if you wish, come and ask for a lesson 6. But I just want to point out that that was worth a mark. Literally what I've just drawn on the screen. So if you come to a question that you're not happy with, don't panic. Take your time, skip it, and then come back to it. But don't, for God's sake, leave it blank. You're right, Kiana. Can I help? You don't understand? I'll mark it for you at the end and we'll see. It could have just been a mismark. We have 70 papers to mark. It gets boring. All right. Just a quick show so I know. Who got 2 or fewer marks on this? 2 or less? 4 or less? 6 or less? Wait. That's everybody. Other way around. Two or less between 2 and 4. 3, 5 and 6? Okay. I'm going to show you what the mark scheme looks like this in just a second. I've got about 6-7 minutes before we get to the end of the session, so I'm going to take my time with this just so you can understand 2 things. How we mark exam questions, how we mark 6-mark questions, and how easy it is to get lots and lots of marks. Figure 15 shows a wooden block connected to a weight by a string. The string goes over a pulley. That's this section over here. The surfaces of the table and the wooden block are both rough. That's going to give us a bit of a hint about what we're going to be talking, about. The wooden block moves across the table at a constant horizontal velocity. So my wooden block is moving over there at a particular speed. Well, velocity because it's one direction. Several vertical and horizontal forces act on the wooden block as it moves. Explain how the forces keep the wooden block moving across the table at a constant horizontal velocity. This is the command that you're given. Explain. Say what's happening and why. You've got to specifically refer to, because they're directing you towards, what comes after the command is the direction. Explain how the forces keep the wooden block moving across the table at a constant horizontal velocity. You should refer to all forces acting on the wooden block. You may add to the diagram to help your answer. I'm going to make 2 lines. I'm going to do 3 lines and 3 labels. Four marks. Yeah. 4 marks. I mean, probably more like 3 if you don't write anything afterwards, but that by itself is enough for 4 marks. 6 marks. That's supposed to be a Q. Equal. Friction and pull are equal and opposite. What I've written up there is 6 marks, 10% of a GCSE. The trick is knowing which words to put in there. So while it looks simple now in hindsight, when you approach a 6-mark question, always have a bit of a plan, have a bit of a think. It's asking me to explain about forces, keeping it moving across the table at a constant horizontal velocity. So I have got to talk about the forces that are pulling my wooden block and the forces that are slowing my wooden block down. The way that we mark these questions is we decide whether or not you're a level 1, 2, or 3. If you've given me a couple of science facts, but they don't really make sense, that's you in level 1. If you've got a couple of science facts and you're linking together these ideas of science with the question they've asked you, that's level 2. And if you have science facts that you can both link together and adequately explain or describe the situation that's going on, that's a level 3. Level 3s can never be received unless you use some kind of an equation, a law, or a figure. We use Newton's third law there, equal and opposite reactions. We could have used an equation if we wanted to. Resultant force, force 1 minus force 2 equals resultant force, if 0, blah, blah. Anything in this box would have gotten a person 2 marks. If they'd said contact, weight, friction, tension, weight, reaction, anything like that, immediately, if those words are in their answer, they get 2 marks. If you can explain, now we're going to take friction as an example. If you can explain the effect of friction, that puts you up into the 4 marks. If you can explain what direction weight is acting, you can go into 4 marks. If you include a law, if this had a graph, if you use the graph, and if this was an equation that you could have, if you could have used an equation in this question, that's what gives you your level 5 to 6. So with your 6-mark questions, here's what you do every time. Bullet points. Use something from your figure. Use an equation if you can. Use a law if you can. And read the question carefully and look at the direction that they're giving you. They want you to tell them how the forces keep a horizontal velocity going. Gravitational potential energy and kinetic energy were mentioned by dozens of people. No marks, because they've directed you to talk about the forces. If they say you may add to the diagram, take that as a you really should add to the diagram. And if you ever add anything to a diagram, don't forget to label. I think that's it. Any questions? All right, I'll stop the recording and then we can have question time. Tell you what, nice way of keeping you all silent, isn't it? Threatening to put your voices on YouTube unless you shush.